Well, hello everyone. This is Mahmoud Al-Lozi, ASU Department of Civil Engineering. I speak on behalf of my team, Dr. Hashim Al-Hindi, Mas Al-Ujaili, and Sahar Khamfar. In the beginning, I want to thank the International Conference Compere and the University of Alanya. Also, I want to thank people in charge for this opportunity. Our study here is about selection of optimal geometry of curved roof trusses based on steel weight optimization. Now, this is the list of content. We start by introduction, objectives and methodology, preliminary design, finite element modeling, discussion of results, and at last, the conclusion. Now, let's start by the introduction. Here we're going to talk about the truss. Generally, a truss is a single plane framework of individual structural members connected at their ends of form a series of triangles to span a large distance. Now, there's a wide usage for the curved roof trusses because of its properties in the side of architectural issues, also its flexibility and beneficial in the space demand. The problem statement. Now, steel construction engineers and designers complain about the lack of a clear principle in the process of selecting cross sections. And this, of course, will affect the project economically, also with alternatives confusion. Objectives and methodology. Now, the main objective, well, it's simply the solution was to find a guideline of selecting the structure geometry. We worked on 4 most widely used trusses, Hu, Pratt, Warren, and modified Warren, where this study demanded 436 models using RVM software of finite element design, which contains feature of optimization in accordance with Eurocode 3. Methodology. At first, the parametric study used these values by making one of them variable and the other will be fixed. Then we're gonna transfer to the modeling analysis using RVM. The information from modeling analysis, we're gonna use it in design results, and we're gonna use these results to confirm a regression analysis study to find the perfect design. And in the comparative design results stage, we're gonna compare them by early design stage projects. In parametric study, this is the front view of every truss, its verticals and chords and diagonals. Modeling stage. In modeling, we use the RVM, number of models by Eurocode, and the shape of the cross-sectional area. Live load was 1 kilonewton per meter square, and the wind speed 39 meters per second as the category C. And at last, we considered the self-weight as the dead load. Last, here how we can model in the drawing stage and the selection of our truss. This is the optimizational stage when we try to find the excellent percentage of design ratio. Here, the first effect will be the truss depth effect. After optimization stage, we put the weight values of each model in the table right here, then convert these values in a graphical form to study the interaction, then determine an equation to facilitate selection of geometries depending on steel weight behavior in each size. We can just substitute the span and the depth values in this equation to find the weight of the truss. And the conclusion of the truss depth effect, the best span length of whole truss is 10 meters or less. Modified wiring will be more economical when span length is 20 meters or more as the chart. And as you can see in these charts, the steel weight increases in line with truss depth. Regression analysis and data results effect of truss panel size. And the panel size is just the same as the depth we found by the graphical behavior, the equation right here by substituting the panel size and the span to find the weight of the truss. Here the effect of truss panel size. Changing the panel size from 0.7 to 2.5 meters has a slight influence on the steel weight for all curved truss types. In order to select a panel size, even the panel numbers should be obtained. Then we need to take care about the branch to cord angle by keep it between the interval 30 degrees to 60 degrees to satisfactory the weld joint. Here the behavior of the panel size. As you can see in these charts. Now the effect of truss bay distance, it's just the same as the previously showed study. In the graph, here our equation about the bay distance effect. Now, we can find by this behavior that the steel tonnage increase in line with bay distance. And a side of regulations shows at this case cause of dead load, live load, and wind load increasing by the bay distance. The best bay distance option is 6 meters to keep the economically feasible the structure. Now, effect of truss elevation. Here we made all of these values fixed and we change only the elevation. We found that in this graph, when we are increasing the elevation, the weight decreases. So there's an inverse relation between elevation and increasing the elevation and the weight. Now, increasing elevation means decreasing steel usage. So elevation should be maximized to the greatest extent possible. As we can see here in these charts, the relation between elevation and weight, it is decreased by increasing the elevation, the weight decreased in every stage of changing intervals of span from 10 to 20 to 30 meters span. Conclusions. In the conclusion, we found that the curved trusses spanning up to 10 meters, whose trusses yielded less steel weight compared to other curved trusses. Modified wooden trusses, on the other hand, are the most cost-effective type for supporting medium to long spans of curved roofs. The comparison of the steel tonnage of the middle truss for curved trusses shows that the most suitable span to depth ratio is between 10, 12, and 20 for the Hu, Pratt, Warren, or modified Warren, with a span range of 10 meters to 30 meters. And it is recommended in the early stages to keep it the depth ratio of 16. Now, by using the comparative diagrams, the designer engineer can obtain the optimal type of curved roof trusses and its optimum geometry. Even the panel numbers should be obtained, then the depth of the truss should be selected so that the angle between the brace member and the cold member should be kept from 30 degrees to 60 degrees. It recommends using a bay distance of 6 meters to produce a light and typical section pure line. Moreover, it suggests raising the truss elevation as high as possible so that it can lead to structures with relatively light curved trusses and an enhanced sense of internal space can be obtained. This is the references. You can find them right here. Thank you for your attention and for any question. I hope it's clear, it's simple, and it is usable. Thank you.